Okay, so tomorrow I'm going to be starting to check daily. So when you picked up two packets, one packet is the notes packet, and the other is the homework pages. Okay, so homework pages. Notice that it says page 55 to 58. Now, what I've done is, year in, year out, I may change the assignments, taking problems, adding it, or removing it. So 55, 58 is for the entire 1.2, but as you can see, the problems are only on the first two pages. So sometimes I may have more pages shown than the problems that are showing up. But just don't worry about it. As long as you're on the same page, you're good. So you'll be pulling problems on page 55 and 56, and you're welcome to I encourage you guys to put your work on a separate sheet of paper so I can see that you're I want to see your steps. Now, some of these problems, there's not a whole lot of steps involved, but if that's the case, you can write directly on the homework page, on the textbook printouts. But especially when we move into the next section and forward, I'll be looking for your work. Okay. So I'll send out a reminder this afternoon about homework. I'm going to check tomorrow, but after tomorrow, I'm not going to be sending out the daily homework. If it's if there's homework over the weekend, typically I send out a reminder after the weekend. I'll want to make sure that students know to finish homework. But usually, if it's a weekday, I'm not going to send out a daily homework reminder. Okay. So we're going to focus on, we're going to move into limits. So limits is kind of like the bridge between algebra and calculus. But once you cross that bridge into calculus, we're really not going to see a whole lot of limits, even though it is a topic on the AP exam. It's still important. But you're going to feel like, come November that you're going to forget about limits, which is natural. But, we're going to come back and review it towards the end of the semester. We're going to see a little bit of it next semester, but really after this unit, it's going to kind of be a little bit forgotten until we need to review again. But starting in chapter 2, we are going to see everything kind of building. We're going to see these building blocks from the previous unit, but chapter 1, a little bit kind of on its own. Okay, so we're going to talk about limits today, tomorrow, Wednesday. We'll have Thursday as review day, and then Friday quiz. You'll see exactly what the quiz will look like in terms of the topics, and we'll do a lot of practice and get you guys ready for Friday's quiz. Okay. Okay. Any questions about this week? All right, so let's move into the notes. Right, I'm going to move into just going through definitions, vocabulary, and then we're just going to be really focused on trying to get through the first 4 pages. Okay, so limits. Limit and function value are very similar, but there are some very distinct differences. So limit is the y value that a function or graph approaches. Okay, so that's the key word that we're going to really have to pay attention to. Okay, not so much the exact y value, but the y value that we're getting closer as the x moves closer to the given constants. A function value is the physical location of the graph at that point, okay, or physical location of the point on the graph. So okay, let me talk about what that means. We have this graph here. This is r of x. If you look at r of x is a function because every vertical line that you can imagine drawing, you're only going to hit one point on the graph, even at this hole, right? So this hole is not defined here. meaning that the graph is defined at 2, but not the whole. So even if I drop a vertical line right here, I'm only going to hit 1 point because the whole is not considered a point on the graph. Okay, so that's a gap that is being filled in at a different location. Okay, so let's start with function values. Okay. The y value of the graph when x is equal to 2. So if I ask you, what is f of 2? Sorry, not f. R. I named this this function R here. So if I look at the graph here, R of 2 is equal to what? 1, right? Not 4, but 1, because that's where the point is. Okay, so that's straightforward, right? Okay, now limits is related to the y value, but there's a distinct difference here. The limit as x approaches 2 of R of x is equal to. So if I want to find the limit as x approaches 2 for the graph, we really want to know how is the graph behaving around the x value of 2. So what I want you to do is I want you to pick a point to the left of 2 on the graph. And then pick a point on the other side of 2, let's say like 2.2 or 2.3 or 2.4. Okay. And now we're going to draw arrows towards our target. Okay. So if I'm starting to the left of 2 and I want to move towards 2, I got to move to the right, but I got to move to the right along the path of the graph. So I'm just going to follow the path of the graph. I'm going to draw an arrow to indicate where I'm headed. And if I happen to start on the other side of 2, then I'll have to move to the left. Right? If I'm starting on the right side of 2, I got to move to the left. I got to follow along the path of the graph. So now the question is not where the point is, but where is the arrow headed to? Are the arrows moving towards the same destination? Yes. Okay. And what is the y value that both are getting closer to? 4. That is the limit. Something that we have to get used to is that the point may be living elsewhere, but as long as you're approaching the same y value from both sides, there's consistency, and that's enough for us to have a limit that exists. Okay. And I like to have those visual arrows showing, because if we see the arrows visually, then it's more obvious. Okay, there must be a limit because I have a consistent movement towards the same y value, even though the y value is living somewhere else. Okay. All right, so in order for a limit to exist, the graph must approach the same real number y value from both sides of my target x value. So if I want to know the limit as x approaches 2, I'm going to start on the left side of 2. I'm going to start on the right side of 2. I'm going to move towards 2 and see if the arrows are consistently moving towards the same y value. Okay, so we'll do a lot more review of this, but I want to start introducing that concept. Now, what are some examples of where a limit does not exist? Okay, so let me go through those examples. Okay. One is where if there's a jump discontinuity. Okay, jump discontinuity is where a graph is moving along, and then you have to pick up your pen or pencil to get to another part of the graph, and you see that the branches are obviously disconnected. 2 distinct, separate branches that's not connected. Okay, so the point in question is at x equals 5. So we'll go ahead and indicate that point there, that x value. Okay. Let's talk about the function value first, because function value and limit are related, but a lot of times they're different. So I want us to begin seeing those differences. Okay. So again, function value, you're just zeroing in at that point. You don't care what's around the target. But limit, you care about what's around the target and not so much about that physical point itself. Okay. Let's talk about f of 5. Okay, if I ask for f of 5, where's the graph? Where is the point? Where does the point exist on this graph? Yep, you see the point, the closed circle is at 1, if open circle is at 2, we ignore the open circle, we look at that closed circle. So that's order pair, right? We know what order pair is, we know how to find a physical point on the graph. Now, limit. Limit again, we want to talk about the approach from both sides, so let's practice that visually. We're going to pick a point to the left side of 5 on the curve. And you may be asking, okay, what point do I choose? So I would say pick a point relatively close. Okay. Not too close where you can't see what you're doing with the arrows, but not too, and then not too far away where other things may be prevent you from getting the correct read. So just pick a point that is relatively close on both sides of 5. This point, I have to move to the right to move towards 5. So I'm going to draw the arrow. This point, I have to move left to move towards 5. So I got to draw an arrow to the left. So now the question is, are the two arrows headed towards the same destination? No. That's how we know the limit doesn't exist. If the arrows are headed towards the same y value, the limit exists. If the arrows are not headed towards the same real number, then limit doesn't exist. I typically use this abbreviation, does DNE, for does not exist. Okay, questions? All right, let's look at example 3. The point in question is at x equals 3. So let's just start with order pairs first. If I asked you for f of 3, what would you say? Is there a point that sits at 3? No. Okay, so there's vertical asymptote. There's no point that sits on that asymptote. So we just say f of 3 is undefined. And I'm doing this because I want us to just begin practicing seeing the distinction between order pair and limit, and the fact that we have a different approach if we're talking about order pair versus limits. Okay, so limit as x approaches 3. So again, we'll pick points on either side of 3. And I'm going to head towards 3 along the path of the graph. Okay, so what is the left branch headed towards? What y value?
Infinity.
Okay, right. It's headed towards the x value of 3, but limit is talking about the y value. So it's going up, right? It's going up to positive infinity. How about this right branch? Same. Okay. So what would the limit be here?
Infinity.
Positive infinity. Now, okay, so let's talk about that for a moment. Okay. In order for a limit to exist, the graph must approach the same real number y value. So is infinity a real number?
No.
It's not. So what we're going to say is we're going to say it doesn't exist. Okay, it doesn't exist. However, we're going to create a subcategory. Okay, subcategory to indicate how the graph is behaving, and we're going to say positive infinity. So positive infinity is correct, but it's also, we have to understand that it's not a true, it doesn't mean that the limit exists. It just means that we're talking about how the graph is behaving in a way that we can visualize it. Okay, so positive infinity just means there's consistent movement towards positive infinity from both sides, but we have to understand that it's a subcategory under does not exist because infinity is not a real number. Okay, questions so far? All right, put a star next to example 4. We're really not going to see this example probably, except for maybe just this one. Okay, but just want to kind of go through the different variations. The majority of what we're going to be dealing with is example 2 and 3. We're really not going to see 4 except for what I'm just showing now. Graphs with oscillating behavior. So there's a strange function here. This is sine of 1 over x. And the limit as x approaches 3, what's happening is the graph is going to keep bouncing between values where it's just never going to settle. So no matter how far you zoom into the graph, it's just going to continue to have this jumbled mess. And because the graph is not settling and we can't figure out where the graph is headed towards, we also say this limit does not exist. But this falls under the fact that some oscillating behavior, it just keeps jumping between values and we just can't get a good read on the graph. All right, example 5. We talked about limits from a graphical perspective. And then quickly, we're just going to do one example of limit from a numerical perspective. Okay? But we're still going to approach it the same way that we did example 1. All right, so let's say we are doing finding a limit without having the graph in front of us. We just have these table of values. And we'll find the limit as x approaches 1 for this function. Okay? And we may not know what the picture looks like, but we're just going to try to decipher the limit based off of what's given. So just like before, we're going to pick points on either side of our target. Okay, our target is 1. So I'm going to pick a point to the left of 1, which we see as 0.9. And I'll pick a point to the right of 1. In this case, the furthest I can get is 1.1. So as I move towards 1, I know I'm moving towards 1 because my x value keeps getting closer towards 1, right? 0.99, 0.999. What's happening to my y value? Can you see a pattern? It's headed towards what? 3. Yeah, headed towards 3. We may not, we see that we don't, or we can kind of use context clues to see that, yeah, 2.9797. If we get even closer, probably 2.9997. But we see it's headed towards 3. Right? How on the right side? As the x value is getting closer to 1, the y value is also approaching 3, but this time from the other side of 3. Right? Now, does it ever physically reach 3?
No.
It doesn't, but is the approach consistent?
Yes. Yeah.
Yes. So we say the limit is equal to 3. Even though the order pair is undefined, the limit still exists. Okay. If you look at example 1, we experience the same thing, right? That hole is preventing us from getting the limit and the order pair to be the same, but here the hole is not filled in anywhere. At the limit, we care about the approach. Order pair, we care about just that physical point. All right, questions? All right, let's look at page 2. I'm going to kind of walk us through these first few examples, and then I'm going to have you guys try the bottom of this page. Okay. So anytime I see limit, we're going to practice doing that. Start with 2 points and make the arrows go towards that target and see if the arrows are consistently moving towards the same y value. If it is, we can identify what y value is headed towards. If it's not, then we say limit doesn't exist. Okay, limit as x approaches -5. So I find -5. I'm going to pick points on either side of -5, relatively close. And I'm going to draw arrows towards -5 along the path of the graph. All right, are the arrows headed towards the same location?
No.
So limit doesn't exist. Okay, let's find -4 on the graph. Okay, pick points on either side of -4. Draw arrows towards -4. So you always have to follow the path of the graph. But here are the 2 arrows headed towards the same destination.
Yes,
Yes, they're both headed towards what?
1.
1. Now, even though the point doesn't exist there, we don't care about it. We just want to know the approach. Right? If the approach is consistent, that's good enough for the limit to exist. All right, number 3, now we're shifting perspective here. Now we just want to find the order pair. We don't care what's happening on -3, we just zeroing in on -3 to see what the y value is. Okay, what's the y value of -3? -2, right? So that's just the point. We see that the graph goes through that point. Okay, we'll pick points on either side of -3 now. Pick a point to the left of -3, pick a point to the right of -3. Make it head towards -3. Okay. Are my arrows consistent? Yes, they're both headed towards what?
-2.
-2. What do you notice?
There's correlation between 2.
Correlation between the two, right? Previous examples that we did, none of them correlated. What is it about this point that allows for the order pair and the limit to be one and the same?
There isn't like a hole there.
So that's the big idea that we're going to get to next week, right? That you're not going to see a difference if the graph is behaving normally, meaning if there's no holes, if there's no asymptotes, there's no breaks in the graph, you're not going to see a distinction because the order pair and the approach is going to be consistently the same because the graph is going to be connected. But as soon as there's any breaks, disconnected graph, then you're really going to see the distinction between order pair and limit. They're going to start giving you different values. But if the graph is connected, they're almost going to feel like the same thing because they're not seeing any distinction. Okay, we're going to use this concept, this information to help us with this idea of continuity next week. Okay. All right, so I just want to give you a little bit of a preview here. Okay, now f of 3, we're back to finding a physical location just at 3. What's f of 3?
Undefined.
Good. Yeah, I see a hole there. I can't say the point is to that hole, but now I'm going to go searching along that vertical line. I don't see anything, right? Nothing is defined anywhere on that 3. So we say undefined. Now, if you say it does not exist, that's fine as well. I kind of use undefined for points and does not exist for limits, but you can mix and match between two, it doesn't matter. All right, everybody good so far? Any questions? All right, number 6, limit as x approaches 3. Pick points on both sides of 3. Follow the arrows. Are the arrows moving to the same spot? Yes. What's it moving to? Number 5 is undefined because I don't have a physical point that's filled in anywhere along 3. Now, if there was a point that was defined somewhere else, then I can pick that point out, but that hole is not good enough for location of that point. All right, number 7, limit as x approaches 6. Pick points on both sides of 6. Are the arrows consistent? No, does not exist. All right, so I want you guys to try 8 through 15. And if you have time, you can go to page 3, but I'm just going to highlight a few problems from page 3, and then we'll go to page 4. But let's do page 2 first. But if you're done and you want to keep going, feel free to do that. But we'll, I'll I'll show the answers for page 2, once you guys all had a chance to try it. Okay, so 8 through 15. So you see how the x value is headed towards 1? Now I'm going to ask myself, what's my y value getting? It's getting closer to 3. Getting closer to 3. It never reaches it, but it's getting closer to it. Here, starting on the other side of 1, my y value is getting closer towards. Never reaches it, but it's approaching 3. They're both approaching 3. That's it. That's what That's not too bad. That's this issues around this. But this limit as x approaches -3, I don't really show up. Then you put down some both sides and you find that the set of -4, what is that -4? That's right. So I would say, because I'm existing self-calculated lots of. That's right. This makes it like all the stuff. I'll go and stop those. It's the same kind of.
Oh, it's just like it's.
No comparison on both sides.
Yeah.
You want a wrong valve. Yeah.
I mean, I said, is that?
Huh?
Okay, guys, check 8 through 15. Are there any ones that you want me to go over with you? I can, go more in detail. Yeah,
Can we put does not exist for undefined, or like, does it matter
it
if?
doesn't matter. Yeah.
Okay.
You can hit flip flop. They mean the same thing.
Okay, cool.
Okay, you're talking about the next page. But before we get to the next page, any questions, 8 to 15? All right, so there's a couple ones I want to kind of highlight on page 3. So if you can go to page 3, I just want to highlight a few of them that we haven't seen on page 2 yet. So it's 18, 19. Now, if you did You did the rest of it, that's fine, just wanna. Okay, so let's look at 18 and 19. All right, limit as x approaches -4. So we know limit, we gotta pick points on both sides of the target. Is the y value headed towards a real number?
No.
No, so we say that the limit what?
Does not exist.
Does not exist, but is there a subcategory?
Yes.
Yeah.
Yes, they're both headed towards positive. Okay. So if you just see positive infinity for limit, just understand that, yes, say that limit is quote unquote positive infinity, but technically it's under the category it does not exist. That's not a real limit. It's just a description of why it doesn't exist or how it doesn't exist. Okay, f of -4. Do we see any point at -4? So no,
Undefined.
it's undefined, yeah. Okay, let's skip down to, actually, there's one more that some of you guys brought this up, so I think this is good to go over 16 there. Okay, limit as x approaches -9. Remember, for limit to exist, we gotta be able to pick points on both sides. So what do you guys think?
Doesn't exist.
Why, what's your reasoning for why it doesn't exist?
Only one point goes that way.
I have nothing to compare it with on the other side, right? So if I have nothing to compare it with, I can't fulfill my condition. I gotta approach from both sides, so if it's an endpoint and nothing is to the left or to the right of that point, the limit's not going to exist, okay? So this would be, it does not exist. Even though the point lives there, even though the graph is connected on one side, I have nothing to compare it to. I can't start to the left of -9, so I can't fulfill my condition for limits. All right, 28 and 30, number 28, limit as x approaches 3, what would you say? Does not exist. Is there a subcategory? Now, we're only gonna have a subcategory if we see a consistent movement. If one's going up and the other's going down, we'll just stop at does not exist. So there's no subcategory that we can quickly say, so we'll stop at does not exist. How about limit as x approaches 7?
It's the same thing.
Same thing, right? Now, if the arrows are both down or if they're both up, I can create a subcategory, but both of these are just be with that. Okay, any questions here? Now, this is the, so this is the easier of the two things that we're doing today. The easier one is where I give you the graph and you just fill in information about the graph. The harder thing that we're going to talk about now is if I just gave you a list of properties and you have to convert it onto a graph, convert it into a picture. The reason that's harder is because there's more variables that exist. There's more possibilities that you can create. So everyone's graph may look a little different and everyone can still be correct. But there's few things that we have to make sure that we are following so that we're not creating something that doesn't work. Okay. So if you guys can turn to page 4. Okay, so direction says sketch a graph of a function. So that's important, function. Meaning that we have to make sure that whatever we create, that it does not fail the vertical line test. So let me point out a couple of things that I've seen over the years that students do so that hopefully you guys don't make a mistake here. You got to draw this out, just look at this from perspective here. If I have a graph over here and I have an arrow here, and I have a graph over here and I have an arrow here, is this graph going to pass a vertical line test? It's not. Okay. It looks like it's fine, right? Because I don't see any conflict. But if I follow those arrows, right, if you draw an arrow, I'm going to follow it see where it leads. And eventually, those lines will conflict with each other and they'll eventually fill the vertical line. So whenever you create a graph, make sure that you're not drawing an arrow towards the graph, right? Because even though it doesn't look like it's an issue, those arrows are eventually going to cause an issue. So if you ever want to create an arrow, which is fine, just make sure that they're exiting the graph. If they're exiting the graph, that's fine, because we know that those arrows can continue in their respective directions, and we're not going to have any conflict with those two lines overlapping each other. So that's one thing. Okay. Okay, so I'm going to point out a couple more things as we look at these examples. Okay. Okay, we're going to go through and try to create something that will work for each description. But I'm going to start off with the easiest things. Okay, I'm going to find the easiest things to do first. And that's the order pair. Order pair will be the easiest ones to create. So number 2, I see the order pair. I'm just going to plot that point. And I'm going to check that off my list. Number 3 is easy as well, -1, 6. Check that one off my list. F of 3 is undefined. So that just means I'm not going to put anything on 3, so that's fine as well. And the rest are limit statements. Okay. Now, this is what I want to do for limit statements. For limit, we know that the graph is going to approach that target y value, but it may or may not reach it. So the way that we can make it safe so that we're not having to decide, oh, wait, I plot a point there, I need to erase it because there's a conflict. If limit exists, we're always going to create a graph that'll look like this. Okay. We'll indicate where that order pair is, and then we'll slightly extend past that point so that technically the limit exists, because if I choose a point on either side of -5, they're both headed towards the same destination, but it may or may not reach that point. But if there's a hole there, the worst thing that can happen is something else tells us to fill that hole in. But if nothing else tells us to fill that hole in, we can leave it blank, and we don't have to worry about erasing and changing a lot of things. So if you see a limit exists, go ahead and put a hole there. And just slightly extend the graph on either side. We don't want to go too far because we don't want it to conflict with other things that's going on nearby. So I'm just going to create a slice segment, and eventually I can make the graph a little cleaner by connecting the parts that need to be connected. But right now, that's perfectly fine. And notice that the hole in this case will be the perfect scenario, because you see the point is defined elsewhere. So that hole is supposed to be there. Even if the point is not defined, it's okay, because we still fulfill that first condition that the limit exists.
And we also know we're not going to connect that point anyway.
Right. This point is not going to connect anywhere because the graph is connected here. It's not connected here, because the limit is telling us it's up where the connected parts of the graph is. Okay. All right. So I can check the first property off my list. Next up, limit as x approaches -3 is equal to -infinity. So what does that tell us? What's happening there?
There are arrows going up.
And there's a what? Vertical asymptote. Okay, so the graph is falling into -3, but it's never going to reach it. We know there's a vertical asymptote at -3. And I don't want to extend too far. I just want to show what's happening right at that point, and I can worry about figuring out the rest of the graph later. But I just want to isolate my property, but I don't want to potentially mess up and cause conflicts with the rest of my graph. Now, let me talk about something that I've seen with vertical asymptotes that I've seen students do. Now, This is what an asymptote looks like, okay? 1, 2, 3, asymptote. Okay, you want the arrows getting closer together, okay? Because the graph is headed towards, as you get closer towards infinity, sorry, as you get closer to the asymptote, the arrows are headed towards negative infinity. But I see some students do this in the past. I see asymptote drawn, but instead of falling into the dotted line, I see students falling away from it. This is not the behavior of an asymptote. Okay, so we don't want to make sure that we don't draw it this way. You want the arrows to get closer to the asymptote, not further away from that dotted line. Now, another potentially difficult thing is number 6. Limit as x approaches 3 does not exist. So let me talk about that here. If a limit does not exist, you have a lot of varieties that you can potentially show. Not everyone has to do the same thing, but here are the options that you can do. One is you can identify that point, let's say it was 3, and you can physically make the graph disconnected from both sides. One branch is headed towards a different destination than the other branch. Okay, that's an example of limit doesn't exist, right? Arrows on both sides, the arrows are not connected. But it's very vague, right? Limit doesn't exist. There's also the subcategory of an asymptote. So I can easily create an asymptote there because that also fulfills the condition, that also fulfills the statement that limit doesn't exist. That's another option. And then third option is, which is similar to this one, I could just have the graph move towards 3 from one side and leave the other side completely empty. I can make it an endpoint. That's also where limit doesn't exist. Right. So if a limit doesn't exist, everyone can have potentially a different looking graph, and everyone could be correct. So you can kind of pick and choose how you want that part to look. But for me, I'm gonna just pick a random target. Oh, and I have to if you want to do branches, I have to make it holes at 3 because f of 3 is undefined, so I can't have anything defined at 3. So I'm just going to have 2 separate branches headed towards 2 different y values. And finally, number 7, the limit does exist, but I want it to head towards 6, 4. Again, I'm going to do arrows on both. I'm going to put a hole there just to be safe, because I know that limit, I only care about the approach. So now if you leave your graph like this, I think that's fine, because technically you haven't broken any rules, but we're just going to try to make it a little prettier, try to get the disconnected parts to show more like a graph. Sorry, guys, I went over. All right, you guys have homework tonight. I'll send out a reminder tonight just to get you guys going here. Don't forget, grab your phones.